Today we're going to talk about Gaussian processes, or introduce Gaussian processes. But I'm going to start with this reminder of multivariate Gaussian properties, and then I'm going to use that to develop Bayesian variants, or so-called Bayesian variants of the models we looked at yesterday, these basis function regression models. And I want to use that to then relate them to Gaussian processes. That's also what you'll be doing in the lab session, looking at the Bayesian interpretation of polynomial models and then seeing how that relates to Gaussian processes. Once I've done that, I'd like to then introduce Gaussian processes in the way that I tend to think of them, which is as distributions over functions. Rather than this sort of long-winded way of writing down that f of x, oh, that one's very hard, f of x is equal to sort of a phi of x transpose w, and then putting a prior over w, which we might say is spherical with covariance alpha, and then saying, therefore, let's look at what f does. Actually just going directly to f, saying, well, I know about the properties of multivariate Gaussians, which we're about to review, and the properties of multivariate Gaussians say, well, if this is a non-random vector, which it is, and this is a random vector, which is Gaussian distributed, then this f is also Gaussian distributed. But what happens is its covariance turns out to be a function of x. And that's clear from this Bayesian model, but you can also start at that point. You can, rather than say, oh, let me define indirectly this function to be this and then this to be Gaussian, you can just say, I want to have a Gaussian joint distribution over functions. And that will be the sort of distribution over functions perspective. Then I'll try and relate the two by talking about how you can obtain this covariance function point of view that we'll look at from basis functions. And I hope you'll see some of the advantages to representing the prior directly on f of x when we do that. And then finally we'll have a little look at some different covariance functions. Okay, I mean, not to labor the point, but I think that this is really an important thing, that the sum of Gaussian variables is also Gaussian. This is why all the linear algebra works. It's why everything stays Gaussian under linear algebra. So the sum of Gaussian variables is also Gaussian, and scaling a Gaussian leads to a Gaussian density, where in the sum case, the mean is the sum of the means and the variance is the sum of the variances. And in the scaling case, you just get the scaled mean and the variance scaled quadratically. Now, in the multivariate consequence of that, as we were looking at before, is because matrix multiplication is just scaling and summing, linear operations, that you can actually look at the multivariate case and see the same thing happens. And the rule in the multivariate case is that if x is distributed according to a Gaussian with mean mu and covariance sigma, then y is also distributed as a Gaussian if y is given by w times x, with the covariance, with the mean w mu and the covariance w sigma w transpose. So that's the same, right? That's just the quadratic form variation of this. So instead of w squared sigma squared, it's w sigma. Remember, sigma is representing the covariance. And what I talked about yesterday is really underpinning that is the square root of sigma, which I think of as r times d, some rotation on a basis. And so what we see is, what we write as sigma is really the equivalent of sigma squared. And what we see in terms of the new covariance is the equivalent of w squared sigma squared. But because it's a matrix quadratic form, the order of the multiplications now matters. So it's w sigma w. You can see the special case of this, if we make everything scalar, just recovers the rule from before. So in a multivariate regression likelihood that we looked at yesterday, we've got this type of relationship. We've got the probability of y given x comma w is actually Gaussian distributed. Now it's Gaussian distributed with a particular mean, and the variance, the covariance, is just independent. That's what the sum means here, that you get a covariance that's independent. Now, what I talked about yesterday is doing multivariate Gaussian priors over the parameters. So we looked at the underdetermined case where we said, okay, what happens if I'm trying to do a linear regression, a standard linear regression with one observation? So we had some sort of situation where I've got one observation and I want to plot a line through the single observation. But that's not enough information because I need to determine two parameters. And what I suggested is, well, you could assume a value for C, and then conditioned on the value for C, you can derive what M is. And then what we did is we actually assumed a distribution of values for C. And we could see that we had no noise, so all the values of M then allow us to go right through here. But then when I said, well, but we really want to assume distributions, why assume M? Why assume C and not M? So you could also like assume a value for M and then learn your value for C. So what we really want to do is assume jointly a value for M and C. And what this guy says here is that we're assuming independent values for each W. So this is independent values. This is the IID noise, independent across, there's a product across N. And so we get this N over 2 out the front. And this is independent values for each W with the variance of being alpha. And we get a product over P. And this sum, instead of writing this sum explicitly here, I could write this the sum of Wi squared. But I've just written that as an inner product. I could also write this one as an inner product too. I could write y as a vector minus x times w, which would also give me a vector, and then transpose the same thing. So it's just different ways of writing the same thing. So now we want to know the posterior. I say once again, sorry, that's from a previous slide. We want to know the posterior. Maurizio mentioned this the other day. He said, because I sort of said, it's actually trivial at this point. Once I've defined, and we'll review that, because of these multivariate Gaussian rules, it turns out to be fairly trivial to write down the implied distribution over y. Because these are just inner product relationships. It's not so obvious in the way I've written it here. Later on, we'll rewrite that to make that more obvious. But they're just inner product relationships. We're putting a prior over w, and w is being multiplied by x. And because this is in effect the mean, what we can show is that that leads to an implied prior over y. But what Maurizio said when I did that is, well, how do you get the posterior? So the posterior is often what people think of as the important object in Bayes. I'm not sure if it's any more important than anything else. But it certainly is the way we transfer information, typically between the training data and the test data. So in probabilistic modeling, I'm going to try and avoid saying Bayes. In probabilistic modeling, if we've got some variables, so the likelihood P of y given x comma w also works for test data. So I tend to think of this y and this x as training data. Yeah, so if I write it like that. And if I want to talk about test data, future predictions, I like to write sort of y star, I wasn't the first to do this, y star, x star, comma w. So this is like, we use the same likelihood, because we assume things are IID, we use the same likelihood for both the training data and the test data. So how do we get information? These are just independent across all the data. So this is a product over I equals 1 to n. So if it's just independent across the training data and the test data, no information travels between them. But in Bayesian inference, it's not really independent anymore, and we'll see that later. And what you've got is, you can ask the question, what's the probability distribution over w given y and x? So given my training data, what's my new belief about what my parameters should be? So I define this prior over w, and this was Bayes' rule that we looked at yesterday. So, well, in fact, this is equal to the likelihood times the prior divided by the marginal likelihood. And here we've got this sort of extra conditioning on x. Now once I've got that, I can combine that distribution with this guy. And I can say what I really want to know. So these parameters, I'm going to argue that they're just a distraction. You don't really care about parameters. What you really care about, certainly in machine learning, that's, you know, what I'm saying is untrue in certain domains. In some domains of statistics, you do worry a lot about these parameters, which is perhaps why there's so much controversy. But if we care just about prediction, and I'm going to drop x now at this point, so x is implicit here, what I really care about is predicting on test data given training data. Yeah? Now, in order to get that here, I have to use the integral over w. I need to, in this case, this is equal to, let me just write this out by standing in front and I'll get out of the way, p of y star given w. Again, I'm dropping x that was in the plot there, given p of w given y, dw. This is a fundamental prediction equation that the posterior information, the information we get, and I don't know, how many people have studied information theory or anything like this? No? No one's done information theory? Yeah, okay, a few. This is actually like a communication channel, communicating information from y to y star through w. So it's like, what's a good way of drawing this? I don't know, in information theory everyone's called Anne and Bob, right? Or something like that. So Anne's trying to communicate to Bob what she's seen on the training data. So there's always a wall, I don't know. I didn't prepare this bit, so this is probably all wrong. And there's someone called Anne on this side and someone called Bob on this side. And Anne gets to observe y on this side, and Bob's trying to make predictions on y star. And they both have this model p of y given w and p of y star given w. They've got that information shared. But there's this communication channel from one side to the other. I call it the TT channel, but maybe it's got a better name. I only started calling it that last week. So there's this thing I call the TT channel, which is sort of band limited about what Anne can say to Bob given she's observed W. So Anne is constrained to do that by talking about distributions over W. So Anne throws Bob this, distributions over W for Bob to now use. So Anne, the optimal way for Anne to do that is to actually do Bayesian inference on W under the right prior. And let's not talk too much about that because we're getting too close to information theory. But there's this communication channel between y and y star that is constrained by the number of parameters we're using. And that's what's going on here, that I'm trying to develop the object. Oh, I didn't want to stand across there. I was going to try and use the mouse. Try and develop the object that that information is stored in. And that's from Bayes' rule, as written here, or very commonly we write it's disproportional to, because this guy on the top is not actually a function of W. Sorry, this guy on the bottom. This guy on the top is a function of W. This guy on the bottom is not a function of W. So while this is really the joint distribution, since the normalizer is not a function of W at all, we know that in order to get the conditional distribution, we just have to normalize this guy such that this thing is a density. And that's sort of the normalization trick in Bayesian inference. What do I mean by that? Well, in the Gaussian case, which is nice and easy, it's kind of easier to see that we've got some, the likelihood is exp of a squared, where a is a sort of linear function of W, and the prior is exp of b squared, where b is also a linear function of W. Multiplying these together gives us exp of a squared plus b squared, which is the sum of two quadratics, where a is a linear function of W, b is a linear function of W. So the sum of this is just now c squared, where c is also a linear function of W. You can just complete the square to recover this. Now, so your result is exp of c squared, a new quadratic. But if this result here is quadratic in w, then we know that, sorry, I was going to do it here, hold on. It must be a Gaussian density. So if it's of the form e to the power of something that's quadratic in w, it must be a Gaussian density. And then we actually know the normalizer straight away. So the normalizer is given by the standard Gaussian form. So we just have to recognize, so the trick when we do these inference things to compute this posterior is to recognize that the result of multiplying one Gaussian by another is also necessarily a Gaussian. And now you think, oh, but I have to compute the marginal likelihood, which we will do sort of separately. But I don't actually have to compute, sorry, I've wiped it off. I don't actually have to compute the marginal likelihood because I know I just have to ensure that W is now a normalized Gaussian distribution, sorry, P of W given Y comma X is a normalized density over W. And the way I do that is just by recognition that it looks like a Gaussian, therefore I know the normalizer. So how is this? So we seem to be avoiding integration. Of course we're not avoiding integration at all. All you're doing is using a particular trick that is, if you know a probability distribution, you also know an indefinite integral. So, for example, if we know this is a probability distribution, so we know that's a probability distribution, we recognize it as a formula, therefore we also know that the integral from minus infinity to infinity of exp minus y minus mu squared over sigma squared is equal to square root of 2 pi sigma squared. Make sense? Because that must be normalized. So when we check the normalization, we know an indefinite integral. Right? So this trick that I'm talking about is really just exploiting that fact. You think, oh, I have to do an integral. But if you recognize that, so you're recognizing that form and you're saying, oh, that's a density. So you could, so it's a shortcut to saying, oh, look at that form, it's e to the quadratic. I now need to normalize the thing because I know it's proportional to, and I look up in a table of indefinite integrals the integral over this, and it says it's square root of 2 pi sigma squared. Or I just think, I know the indefinite integral, I know the normalizer because I know that this is a probability distribution. Does that make sense? So this trick is used all the time when you're doing conjugate pairs in Bayesian inference. A conjugate pair is a case where in this distribution here, you have a certain functional form for your prior. If the likelihood is conjugate to the prior, then you recover. Sorry, you need to do it over here. If you've got a particular functional probability density for your prior, if the likelihood is conjugate to the prior, the posterior will also fall in the same family. So that's a conjugate pairing. The Gaussian example is conjugate because it's Gaussian prior plus the likelihood leads to Gaussian posterior, but it's somehow, I don't know, it's superconjugate because the likelihood is not superconjugate, I made that up, but it's something beyond that because the likelihood is also Gaussian. This weird property, I don't know any other density for which that's true. Maybe there is one. It'd be cool to know if there was one. So prior is Gaussian, likelihood is Gaussian, posterior must be Gaussian. This is a conjugate pair. And the way we do these integrals is to get this thing in the right form that we recognize it looking like that. And therefore the way to do that is to actually complete the square. But we do a multivariate completion of the square. So what we do is we say, well, the log of, if we want to say the log of this, then because this is proportional to, we're just getting a plus a constant on the end. So the proportional multiplying factor becomes an additive constant on the side there. So the log of this distribution is just equal to the sum of the logs of these two distributions. But I've actually multiplied out the contents of this likelihood here. And I did it in exactly the same way that we did it yesterday for maximum likelihood, yeah? So in maximum likelihood, this, I mean, every year my master students confuse this. I tell them to do a maximum likelihood derivation. No, I tell them to do a Bayesian thing, and they write this down and then they start taking derivatives. I don't know why they do that. And every year I emphasize it, and every year I get answers where they do this. So the difference is you don't take derivatives once you've written this down. In the maximum likelihood, you write down the log. In fact, it's the log likelihood, so it's missing this term. The log this is the sum of the log likelihood plus the log prior. What you do is you write down the log likelihood and then you take derivatives. And we've got this special form, so we recognize it as a quadratic form and solve it. It is interesting that in Bayesian inference, it's about integration, and maximum likelihood is about differentiation. It's quite odd. I don't quite understand the duality of that, so I won't say that any further, but I always think that's funny. But what we want to do now is not take derivatives. What we want to do is complete the square to get it in a form that looks like this. So completing the square to get it in a form looks like this. What do I have on the next slide? Oh no, I've gone backwards. Yeah, shall I write that out? Yeah, let me write that out. Because it's a commonly used sort of thing. So I've multiplied out the top term, and I've got 2 bits that involve W. Sorry, 3 bits. The linear term in W and this 2 quadratic terms in W. But I want to get this density in this form, right? And this to get it in that form, I have to match it to minus y minus mu, c minus 1, y minus mu, where I've got subscripts, have I, of W, W, W. So this is the form I'm trying to match it to, which is also a quadratic form, but this quadratic form is in the way that I expect the Gaussian to be, with a covariance and a mean, which is what I'm interested in. So I need to match that to the quadratic form written above, to this guy here. And to do that, let me just multiply out this form. So I've got, let me put the half in as well. So I end up with minus a half y transpose c minus, sorry, why have I written y? I'm supposed to be writing w. As I was going down that road, I realized something was going to go wrong. But you guys are all supposed to be shouting out, don't you mean over y, or whatever. Like this. And then, so that's from the w, missing transpose, w transpose cw minus 1 w. I've got another term here, which is mu w transpose c minus 1 w. And that ends up appearing twice. And because CW is symmetric, that ends up just doubling itself. So I end up with this plus mu W transpose CW minus 1 W. And then I get a final term, which is minus mu transpose C minus 1 W mu, with the factor of half in. Sorry, keep that W small, mu. But this term is constant in W. So what I can do now, what I need to do now is ignore all the terms that are constant in W, because they're additive constants, and when I exponentiate, they're just going to be multiplicative factors. But I'm getting rid of the multiplicative factors by normalizing. So I can ignore this term here, because it's constant in W, and I can ignore this term here. So what I need to do is match this linear term to the existing linear term here, and match the quadratic term to this quadratic term here. This combination of 2 terms. Actually, you always match the quadratic term first. It turns out to be simpler that way. So the quadratic term we've got on the board, rewriting it out, is minus a half W transpose. And I'm bringing the sum inside, the same trick we did for maximum likelihood. I equals 1 to n, xi transpose. W, but I don't want to write W yet, because I've also got this W transpose W term. So I'm going to bring that inside. Oh, and no one said I'm missing my divided by sigma squared. So I'm going to bring that inside, so that's going to be 1 over alpha I. Yeah? So I've now completed this match, actually. I've taken this WW, that's just collecting the quadratic terms, and I can now match them to this CW. So I now know immediately that CW is equal to Now, I want to rewrite that. How do I want to rewrite that? We did that yesterday.
Transpose X.
Excellent. X transpose X. So sigma to the minus 2 X transpose X plus alpha to the minus 1 I. Missing one thing because that's C inverse to the minus 1. Can you see that there? Sorry, yeah, people are looking around. So that's C inverse, right? Now this linear term is a little bit more complicated because what I need to do is match mu C inverse to what I'm seeing here, which is the sum over yi x transpose, but of course we'll rewrite that x transpose y, capital X transpose y. So it's slightly more complicated. Basically you extract, well, you don't have to extract C first because you don't tend to rewrite this bit out. But in order to get the linear term, what I need to say is, so matching the linear terms, I just want to say that mu, well, let's write the transpose of this because W transpose CW minus 1. The reason I can do that is because, of course, this thing is scalar, so I'm just transposing a scalar to do this. And I want to make it equal to 1 over sigma squared, so let's write that as sigma to the minus 2. Then I need to get the x and thing the right way around. So let me have a pause to think.
W over the sum, W transpose.
Sorry, so, I'll come back to that one. I'm just thinking through this bit. So what was that, sorry?
No, it's okay. No, it's
okay.
then you have to transpose.
Oh no, I did that. I just did that the wrong way around, didn't I? W transpose x transpose y. Yeah? Now, I recognize that the thing I'm multiplying by here is just equal to this. Well, times sigma to the minus squared. So actually, you can't always do this sort of cancellation. Be careful about this. But that doesn't matter, right? So then I get mu w is equal to C. I'm going to multiply both sides by CW. CW, let me leave the sigma squared in. Sigma to the minus 2 CW x transpose y. Yeah? So that's the mean of the posterior distribution. And this is the covariance of the posterior distribution. And I've got my posterior. And I'm missing an I in here. Yeah? So there should be an I inside here. Who was it? It was you that pointed out yesterday. Someone pointed out yesterday the algorithmic issue that how you could add diagonal terms. I mean, what I just wanted to sort of pause and look at is that this was the maximum likelihood solution we looked at yesterday, and this is the new posterior mean. They are identical up to the presence of this alpha to the minus 1 should be a capital I in here. So this piece here. If you eliminate that piece, then they become identical. Now the way you eliminate that piece is by driving alpha to infinity. What happens then is that the sigma squared that appears here also appears here and cancels. And you just recover the maximum likelihood solution. So if you think about what that means, if you say alpha is infinity, what you're making is your prior is really, really flat. It's actually an improper prior because it's no longer a density anymore. But as alpha goes towards infinity and you become very uninformative about the initial value, you recover the maximum likelihood solution in the mean. So that's sort of worth bearing in mind. Now, the likelihood is computed as a normalizer, but I don't want to go through that computation. We could do the likelihood computation. And in fact, in general Bayesian inference, you have to do the likelihood computation. So in general Bayesian inference, the way you do the likelihood computation is you actually have to do the same thing. So you start with this guy here, this joint distribution, and then you integrate out W. But it's a rather involved process that involves using the Woodbury formula. And I'm going to show you another way of doing it that's much simpler. So we'll ignore that for the moment, but the marginal likelihood, so I've conditioned now on all the additional parameters that are there, because obviously the marginal likelihood is dependent on x, it's also dependent on these parameters of these prior distributions, this alpha, and it's dependent on the noise. We haven't integrated those out. So the marginal likelihood turns out to have this form. It's a Gaussian. Now, if we go back to the polynomial data, and you'll do this, I think, in the lab class, you can now do a Bayesian fit of the polynomial data. Now, one thing that I think is important here is to see a couple of things. People get confused about Bayesian inference. They think that the error bars on the model are sort of magical. And they're typically not magical. So I'm showing error bars here for, I think, if I remember correctly, 128. Let's look. No, I fixed sigma squared here to a small value. So I think I've fixed sigma squared. I can't quite remember how I've done it. But basically, I'm purposefully showing very small error bars. Because one thing that does not happen is, which people get confused about, is the posterior does not carry any uncertainty that is due to model incorrect specification. So that's important, so I'll say it again. The posterior does not carry any uncertainty that is due to model misspecification. So what do I mean by that? And it's actually easy to see this in the covariance here. So here's the covariance, again missing the I. What happens to this covariance as we observe more and more data is that this sum gets larger and larger and larger and larger and larger. So because it's inverted, this thing gets larger, but what gets large is not the actual value of the covariance, it's the precision, the inverse covariance that gets big. So as you observe more data, what this means is you have a covariance and notice y doesn't feature in the covariance, which is slightly odd. Why? The observations do not feature. This is key to this point here. But as you observe some data, so if you observe two data points, if the data points were sort of one data point's out there and one data point's out there, actually this is just the basis of a covariance, right? So we would just have a sort of posterior like this. It's just in the same way, so because it's x transpose x, it's a factorization of a covariance. But then what happens, you might still have that same shape. As you observe more and more data though, you don't have any divide by n. So this thing gets larger and larger and larger as you sum all these things up. So the inverse, the covariance gets smaller because the inverse covariance gets larger and larger and larger. So what that means is that in effect, these things become more and more confident, tighter and tighter and tighter, and they eventually become a delta function, effectively. As n goes to infinity, you become totally confident about the posterior. So if you observe enough data, if we observe infinite data, this covariance here becomes 0. Approaches 0. Because this sum increases with n, and then this is inverted. So you get a point estimate, just like we had in maximum likelihood, centered on the mean. That means there's no uncertainty in the linear case. So remember before when we introduced this example, we said, okay, we get this example of one data point and we've got all sorts of uncertainty going through it. That sort of uncertainty with infinite data just disappears and you are back to the maximum likelihood solution. So with infinite data, in the linear case, you would just have a straight line and be 100% confident of what that straight line is. Now, notice that none of that discussion involved talking about what y was. So if y, if the actual underlying function, so if we do have infinite data, so look, I can draw infinite data with a pen, that's quite nice actually, isn't it? That's infinite data, right? Continuous amounts of data. So if that was all my data, infinite noise-free data, I would just end up being 100% confident that a straight line goes through it under the Bayesian side. Now, of course, when I come to compute my noise, if I come to compute sigma squared, I'll find that sigma squared says it's like that, but with the noise being wide like this, yeah? Because that's the model mismatch term. The noise has to take account of the model mismatch. But there's sometimes, I see again and again, confusion about what would happen in this situation if you just ask someone meanly in an interview. You say, what would happen if you've got the wrong model? What would happen to the uncertainty, the error bars? They always say, oh, well, then the error bars would go large because it would see that it's got the wrong model. That does not happen. If you have the wrong model, which is what we have in this case, it just screws up. Yeah? You become massively confident about the wrong thing. And this is why model specification in Bayesian modeling is so important. That if you get them on, so having these error bars is great. And I show you my favorite. We go back to the sort of motivating original example with one data point doing a regression in this space. If we look at the error bars, they're brilliant. They say they don't really know where the function goes, either side of the data point, but it goes somewhere. Marginally, the error bars look great. If you look at the correlations, obviously, if it was a nonlinear function, the correlations wouldn't match. But marginally, these error bars look really good. Because with very low data, you haven't exposed how incorrect your model is. So you always kind of have to have a model that's more complex. You know, if your data gets too large, it can reveal your model to be wrong, and then these error bars, they're no use anymore. So that's just a sort of labored word of warning on that. Now, that's what we're observing in these examples here. So because I've kept the noise low, I'm not allowing the noise to show. It's incredibly confident. It's modeling this data in a Bayesian way with the mean. Yeah, so it's a zero order polynomial, so it's just doing an offset. So it's just actually doing Bayesian inference on the mean of this data. So it's totally confident now about this function being correct under the posterior over W, because if you observe that many points, you know the mean pretty well, actually. It doesn't take long under Gaussian assumptions to define the mean. Of course, if we were to show the variance would be larger. But as we go through, we'll see that that continues to be the case. These here, the uncertainty we're seeing here is due to uncertainty about the gradient. There's somehow, I have set, yeah, so there's some uncertainty here still. There's not enough data to make it totally collapse on the posterior. And as the model gets more complicated, the uncertainty stays sustained. So now we're going up to sort of a fifth order polynomial. Sorry, I didn't really describe that the center line is the mean, and the outer lines are one standard deviation. And when I say one standard deviation, I mean they're one standard deviation of this object I said was the most important object, which I believe it to be. We're looking at marginal densities of this object. So we're looking at the mean, in this is the center line, and I think, well, maybe two standard deviations of the Gaussian. This turns out the result of this is Gaussian, because it's a Gaussian posterior combined with a Gaussian likelihood, and we're looking at the mean of that Gaussian and two standard deviations either side. Of course, there's structure in this Gaussian, which we're not observing. And you should always remember that. When you look at these functions, we're just showing the marginal error bars sort of like that, but with a continuous line. But there's also structure. So, for example, if I later said, well, I'm worried about what happens when the function comes out here, then if I conditioned on saying the function comes out here, it would do something to these error bars at this end. They would move. So thinking about that, it's more obvious that in the linear case. So in the linear case, obviously, if I conditioned that the function's here, since it's a straight line, then I know that the error bars would collapse at this end here. Yeah? So you can't observe that correlation. All you see is that marginally things increase outside from the middle. Yeah? But it's still a nice way of observing the data. Any questions at that point? You're going to do this in the lab.
Can you repeat again what is the interpretation of the covariance of the posterior density? I mean, when the covariance of the data go to 0 or go to infinity?
So the covariance, the precision, yeah. So I'll repeat that again.
When the last equation.
That
one.
So here, okay, so in fact this is actually, so it's nice that you've said that, because I'm going to say it in a different way and hopefully not confuse things by doing that. So X transpose X is the object we're looking at, and we want to know what happens to X transpose X as we go to infinite data. Now remember that X transpose X is the sum of xi transpose. I equals 1 to n, yeah? Now let me say as well, well, we talked yesterday about things you could do to your input. You could scale your input, or you could center your input on the polynomials. So let's presume someone's done that. Let's presume someone's centered all our input data. They've subtracted the mean off all the input data. So this is mean-centered data, which I sometimes like to denote like that, but we can also write it like this. So what do you recognize this object as now? Anyone? Covariance, did someone say? Yeah. That's the empirical covariance of the data. Oh no, it isn't, because there's something missing. 1 over n. So it's the empirical covariance, which let's write that as S. So X transpose X is equal to the empirical covariance of the data times n, where n is the number of data points. Yeah? Now, in this formula here, n times s, as n goes to infinity, dominates, and alpha typically gets knocked out. So what you get is, you get n times s inverted. So you get the precision of the posterior will be n to the minus 1, s to the minus 1. That's the covariance. This will be the covariance of the data. N to the minus 1 of the posterior, the covariance of the posterior. So this is the covariance, the sample covariance of the data, but the covariance of the posterior is the inverse of that, scaled by 1 over n, with this term alpha being ignored. So in other words, as we go to infinite data, this covariance of the posterior drops to 0. Yeah? So that means that instead of having this situation where if you're looking at M and C, which is what we did effectively before, we looked at the log posterior when we're doing maximum likelihood, having something that looks like this, then you actually end up with something that is just a delta function at the center. By the way, in order to do that diagram in a way that plotted nicely so that you could see these contours, I think I had to keep n down at about 4 or 5. Because even if you start, if I used this, I initially wanted to do that diagram we did yesterday on this data. Even at this data set size, this is the, remember yesterday, ding, 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 whatever, yeah? Even at this data set size, the contours on this were too tight to see. And the reason is because they scale at n. So you get a factor of 27 on the precision, or 1 over 27 on the covariance. Other questions?
What suggestion would you give us to estimate sigma squared, alpha, and all those?
We'll come back to that when we go to Gaussian processes. Because what I'm going to try and persuade you of next is, well, in the lab actually, broadly speaking, the lab's quite long today. But you can do it in your own time as well. What I'm going to persuade you of in the lab is these aren't good priors over functions. Once we start viewing them as Gaussian processes, they're not good priors over functions. I mean, the reasons being for things we talked about yesterday. So I think well, we're going to stop in a moment. But how we do it in practice is actually this marginal likelihood. So if anything about Bayesian inference, where's it gone? Marginal likelihood. Boop, boop. Oh, there. this guy here, this is why I think the whole thing of likelihood and prior is a bit confusing. Because now this marginal likelihood here also has an interpretation as a likelihood. Yeah? So it's just a new likelihood, but notice it's correlated over y. So it's not independent over y anymore. And that's the thing I'm going to try and persuade you, is that moving away from this IID assumption, which is what happens in a Gaussian process, is a good thing. But it's just a likelihood. It's still a likelihood even if it's correlated. And in order to find alpha and sigma squared, we just maximize the likelihood with respect to alpha and sigma squared. Now, in general, once we start getting into Gaussian processes, we can't do that just by writing down some fixed point equations. We have to start doing nonlinear optimization. So nonlinear optimization is not something we're going to cover at all. In the lab class, you will just run a function model.optimize. And underneath, you can switch in different scaled conjugate gradient optimizers, BFGS optimizers, whatever you like. It's an entire subject on its own. Alternatively, you might want to, and there are certain situations, we'll see one later on this morning, where you actually want to put priors over alpha and sigma squared. So you may not have enough data to even determine the parameters of this thing here, and you may want to put priors over that. And then people use like hybrid Monte Carlo techniques or just sampling techniques in order to estimate those things generally. But yeah, so this is one of the problems with this probabilistic modeling framework, and perhaps why I'd like to think of it more as probabilistic modeling rather than something like Bayesian inference, is at what level do you stop? So we've put priors over the parameters, and we've ended up with a new likelihood and new parameters. So we could now put priors over those parameters and try and integrate them out and end up with a new likelihood and new parameters associated with those priors. And in fact, every time we do this, we're choosing model distributions, right? We're choosing particular distributions from certain families. And there's infinite different families we could be choosing distributions from. So while the probabilistic modeling framework is very elegant and nice, it doesn't solve the problem of model choice totally. It actually turns out it only allows you to compare two different models under a different data set, because you've got infinite choices of modeling you could use for this data, and you could keep going on integrating out, integrating out, integrating out. So I used to say that I'm a pragmatic Bayesian, and what I meant by pragmatic Bayesian is that I integrate until my head hurts, because integration's hard, and you can only do it once or twice before you give up. But then I think everyone's a pragmatic Bayesian, because everyone does that. They integrate until their head hurts, but some people's heads hurt much later than others. So you'll end up with people building these hierarchies of priors. So some people call them hyperpriors. But that's why I think the terminology is not that useful, because all you're doing is just specifying probability distributions over things. So in this simple case, it's kind of reasonable. You can see this is a likelihood and this is a prior. And this is marginal likelihood, and this is a posterior. But if we do another level of Bayesian inference on top of it, what do we start calling everything then? Some people then call this, Jack Good used to call this the type 2 likelihood, because it's a once marginalized likelihood. But that's within the days when he was working at Bletchley Park. So I think Alan Turing and Jack Good used Bayesian inference to decode German codes. But they were all doing it by hand, or I think they were using perhaps their computers. I don't know the details. But they couldn't do any more than one level of Bayesian inference. So it didn't matter that you had these terms. But nowadays, people do many, many levels of Bayesian inference. So I'm not sure how useful these terms are in general. So I just like to think of it, let's put probability distributions over parameters. Let's define likelihoods. Let's combine these things and then get an answer out. Other questions? So I'll just show you the result of what happens now when we do some holdout data in this case. So we get this sort of nice effect. Although the gradient's too strong here, we've got these error bars. Now, I'm not arguing too strongly. This is not the correct model, right? If we'd had observed more Olympics, this wouldn't happen. We would just become super confident that it was going down. But in this case, it looks like we're getting something that it's uncertain about the gradient, but it's not uncertain about the gradient because it's seeing the curvature, because that uncertainty has nothing to do with y. So always bear that in mind. People make that mistake. This case here, it thinks it's going up, but it could be going down. Yeah, this is the sort of thing you want. This is the quadratic fit, right? So the quadratic fit is even quite uncertain in terms of what's happening to this function. We're observing the likelihood of the held out data. And the really nice thing you'll observe is that that doesn't actually change that much. So before, we had catastrophic failure of the models. They began to overfit. Yeah? Because each model was very sensitive to whatever data it was dealing. It's called high variance in the frequentist domain, this bias variance dilemma. So the argument is that these models here, they don't fit well because of bias. So they don't fit the data well enough because they don't have the capability of approximating that function. That's called bias. I'm not going to go deeply into the bias variance dilemma because I'm not sure how useful it is in the overall probabilistic modeling, but it's just how a frequentist would talk about this. These data here can fit these other models. They've got the capability to fit the functional form of the data, but when we were doing non-Bayesian inference, they tended to over-interpolate or something, overfit, people called it, right? And the reason for that is because the parameters weren't well determined. So you're in a sort of, conceptually, you're in a situation where you would have a posterior over parameters, which was rather broad, and you're in here, that's the maximum likelihood solution, or it's probably not quite at the mean, it's somewhere over here, and that's associated with one particular sixth order polynomial. But now we're considering all the family of maximum likelihood solutions all around that density. So we're averaging over that polynomial, which went exactly through the data at some points and therefore got a high likelihood. But then there was also another polynomial that, now it's going to be really hard to draw this, that did sort of this. Yeah? Had the similar likelihood, so it's not dominating very much over this one, because it's actually going through all the points pretty much the same. So it's sort of over here in this space. And it was just ignored before. But in Bayesian modeling, you do this model averaging effect. I mean, that's what people talk about it as. It's a natural consequence of the model. You're considering all models that fulfill the data. It's a good way of, in some way, a nice way of thinking about Bayesian inference sometimes is like, you've got a method of generating functions. So you've got some approach to generating functions. In this case, it's take a polynomial basis, multiply it by a random vector of weights, and then draw the corresponding function, right? So this will generate infinite different functions for you. But you've also got some sort of data. Now, exactly the process of Bayesian inference is to generate all infinite functions. Takes a while. And then throw away every function, or sort of downweight, not throw away, downweight the functions according to the likelihood. So if this function here, actually that one's pretty close, goes through the data, I think this function here is a pretty good one. Yeah, happens to be pretty good. I did that blind as well. Certainly much better than this one here, which misses the data completely at several points. So you sort of downweight that one and upweight this one. And what you're really observing by the likelihood, and what you're really observing is the new population of functions at the end, which actually, it conforms to your prior, like it's something that you generated. So your prior is like your belief before you saw the data. It conforms to the prior, and it also conforms to the data. So you get this posterior.
So when you do not know the likelihood, then you can, that's the idea behind ABC, yeah?
That's exactly the idea behind ABC. Yeah. So there's something called approximate Bayesian computation where they do exactly this. But it's approximate Bayesian computation because they don't know the likelihood precisely. So they throw away...
What they have is the data. So what they do is that choose the functions that go with the data.
And in ABC, so what you do in ABC is you sample a bunch of functions you have, so ABC, just to give you some background, here we've got a prior that is a nice mathematical thing. Imagine you run a large plant, right, which manufactures widgets. And you want to do some Bayesian inference on your plant. And you have a very good simulation of your plant. You know that the widget takes this long to do this thing. But the simulation, while you can write down the simulation as a program, in fact, it was written by someone who's not mathematical at all. It's just written by someone, perhaps, someone who watched the process in the plant. So you can't write down, it is a probability distribution. An example I like to give when I talk at schools is, has anyone ever played Minecraft? Minecraft generates worlds. It's a distribution over worlds. It's just not one that you can write down. Because it's coming out of the computer, it's a distribution, and all simulations are probability distributions. You just can't write down the likelihood associated with them. So what they do in those cases is exactly this. They simulate from the computer program, and then they see how close the simulations are to the data. And the correct thing to do is, if the simulation matches the data exactly, keep it. If it doesn't match the data exactly, throw it away. And that's provably correct Bayesian inference. But that you never get a simulation that matches the data. I mean, it was just luck that one matched the data. And then, even then it didn't match. Look, it didn't match this point up here, the one that I colored in. So what happens is you never get simulations that match the data. So they have a sort of soft matching, and so it becomes approximate Bayesian computation. But it's a nice way of thinking about Bayesian inference in general. It's true in general. But it's just in this case we've got cleaner maths. We can do it all analytically. We don't have to sit there waiting for a computer to do all these simulations. We can get the answer to this analytically through linear algebra. This is our updated population simulations. So it's much, much faster. And there's really interesting work going on by colleagues which is trying to combine things like that ABC approach with these Gaussian process models to try and improve speeds. Okay, so I ran on a little bit longer than there, but just check if there's any final questions before we break.
So do we actually use this Bayesian formulation of the linear model? I mean,
yeah, I think people do. Yeah.
I mean, for example, these people doing like
generalized linear models, yeah.
Yeah. So what about the computational complexity?
We'll come, yeah, we will come back to that. But the computational complexity of this is equal to it should be n m squared, where m is the number of basis functions, I think. Is that right? I haven't thought about that, but I'm just looking at the formula. So the computational complexity, it depends whether your number of basis functions is larger than your data points. Computing this matrix in a product, I think, is m squared, where m is the number of inputs or features you have, and n is the number of data points. So we're talking order nm squared.
But inverting it should be like n cubed.
Yeah, that's why I said as long as n is larger than m. Inverting it is order m cubed. But if n is larger than m, this dominates. If you have, which we could have. Now we're in the world of Bayes, we could have a case where m is larger than n. An over-complete basis, that's sometimes called. You've got more basis functions than data. That was the motivating example. But often people are in that case. So depending whether n or m is larger, that dominates. And I'm kind of making that up on the spot, but I think it's right. It's not a fact I had in my head. Other questions? Okay, so what we're going to do after the break, so I put some reading in here, the slides are already online today, been a bit more efficient, is move on from that to Gaussian processes, and we'll sort of show how those models are Gaussian processes. Or alternatively, have people, well, I don't see people having their laptops. Do people have their laptops here? We've got a choice, actually. We can start the lab, and then in the lab class, you'll be going through what I've just told you about with polynomials. It's the first part of the lab class, and then we can come back. And that means we'll be doing lectures in the afternoon as well, instead of during the lab. So we can try intermingling the lectures and the lab if you prefer. It's up to you. Who would rather start the lab? Hands up if you would rather do the lab portion now. 3.5. There was some uncertainty. Hands going like this. I don't know. I'm calculating that as 7 plus or minus 2. Hands up if you'd rather carry on with lectures now. Okay, I'm counting that as 0. Okay, right. So unless there's any objections, given people, real humans actually update their beliefs given having observed data. So unless anyone's got some sort of thought, so if someone, for example, doesn't have their laptop here, okay, so I suggest what we do now is we break, and then we'll come back in, and we'll do the lab class on the Bayesian Inference with polynomials.
We'll ask again the question, because maybe after the break.
Yeah, maybe people will have updated their, yeah. Okay, good. Right.